Coming up on This Week in Radio Tech, I'm going to talk about something that's going to hit you right in the face pretty soon, and that's PTP, Precision Time Protocol Clock. We're talking to Greg Shay and Sean Dolan along with Chris Tobin about this. Coming up next on TWiRT. This Week in Radio Tech is brought to you by Broadcasters General Store with outstanding service, savings, and support online at bgs.cc. By the Ruby console from Lavo. See Lavo in your future at lavo.com/TWiRT. By Angry Audio. Audio problems disappear when you get angry at angryaudio.com. And by the Calrec Type R console system. Type R is a brand new, modular, expandable IP-based radio system from Calrec Audio. Hey, welcome into This Week in Radio Tech, the show where we talk about everything from the microphone to the light bulb at the top of the tower. We've got an awesome show today because I've been so lucky to get a couple of experts on with me and Chris. Now Chris and I know a few things. Well, Chris does. I'm just here to keep everybody rounded up. We're going to talk about PTP clock. PTP means Precision Time Protocol. And we'll get into all that in just a few minutes. We're going to introduce everybody, give you a little bit about their credentials, and tell you why PTP clock is something that we as engineers had really better pay attention to and understand because it is critical. It's not all complicated. Well, it is under the surface, but as implementation, it's not all that complicated, but we got to do it right or else we're going to be very, very sorry. All right, let's bring in, I'm in my usual place. I'm at the Telos Alliance studio in Nashville, Tennessee, Music City, USA, and very grateful for the Telos Alliance to provide some of my gear and the time it takes to do the show. Thanks a lot to Telos and all the great things that they make. Telos Alliance at telosalliance.com. Now let's bring in my co-host, Chris Tobin. He's at some undisclosed location in the greater New York City area. Chris, how you doing, buddy?
I'm doing well. I'm at a friend's place right now. We're just working on a project, actually using audio over IP for distributing IFB for a TV station here in town. So it's a lot of fun. Having a good time.
All right. That sounds cool. And thanks for, we'll do this quickly. Hey, joining us from his palatial office. Yes, he's got one of the good ones. the chief, are you technology or science officer, Greg Shay?
Chief technology officer.
Okay.
Here in Cleveland. And I do have a window in my office. So there you go.
I know you've got, not everybody has one of those. Yeah,
that's true. In fact, we have some offices down on the first floor where there's a window, but there's no outside. We're not quite sure how the sunlight reaches.
And I understand that you and John Makeley, also at Telos, are still working on perfecting the BOIP technology with the brewery next door.
That's true. For months when they were building the brewery, we had thoughts as we heard the jackhammers to stick a pipe through the wall and tap into their operations. Hasn't happened yet.
Hasn't happened yet. Oh, well, we'll get that beer over IP technology perfected. It probably doesn't need PTP clock as it's an analog technology using analog equipment. So Greg Shay, welcome in. You've been on the show before, and you're going to be explaining some things that we need to know as broadcast engineers about PTP clock. Also with us from, I think he's in an airport in Chicago, Sean Dolan. Sean, welcome into This Week in Radio Tech.
Hey, thank you for having me. Yeah, joining you from the palatial Minute Suites here at the Philadelphia International Airport. It's quite nice.
Oh, you're in Philly. But I heard Chicago somewhere in your itinerary. Is that where you're headed next?
That's where I'm headed next, right. Head back home.
Okay. Good deal. Well, Sean, let's give just a moment to Sean. Sean, you're new at the Telos Alliance, and I originally asked you to come on this show to talk about PTP clock, and so you'll be participating as we are, telling us what you've learned in the field, and also probably learning a few things from Greg. So this is an all-around great show. But what's your new job at Telos?
I'm a support engineer, working primarily on the VX, doing a lot of VX implementation in the field. That's where I am today. I was lucky enough to work with a major network TV station to implement VX at their facility here outside of this area.
Oh, awesome! That's very cool. All right, so if people talk to the Telos Alliance about they need to elevate it up to a higher level on their support call, or they want to talk about implementing a complex phone integration, then they may very well be talking to you, right?
That's right.
Good deal. All right, we're going to hear from everybody as we move along. First of all, our show, This Week in Radio Tech, and our PTP Clock show is brought to you by the folks at Vox Pro via our friends at Broadcaster General Store. Let's hear from Vox Pro. We'll be right back.
Yo, what's up? Live from NAB 2018. Hey, it's Caden. You need to check out Wheatstone and Vox Pro 7.1. The upgrades are amazing. If you're a jock, if you're a talent, producer, whatever, morning show, everyone knows Vox Pro, everyone uses Vox Pro, everyone loves Vox Pro. But now the features for this year, 2018, on 7.1 are amazing. If you're using version 4.5.6 and you go to 7, this is exactly what you're missing right here. The features are a game changer. It's going to cut down your editing time by like 80% depending on what you use Vox Pro for. And with version 7.1, introducing unlimited Practic button bars right here, hotkeys right here. I'm going to show you coming out of a song.
Bad things. It's a lot of bad things that they wish and they wish and they wish and they wish.
So you're coming out of your song?
Yeah.
Start your next song right here. It's basically an entire production room right on Vox Pro. So it's the Vox Pro we know and love with a ton more features. And now this is the ultimate game changer right here. Effect macros. So instead of hitting your effects button bar and going up here using your mouse for every effect, you do it right here with one click of the mouse, and you're going to cut down your editing time by about 80% without even touching this new sexy black controller. Check it out right here, Wheatstone Vox Pro 7.1 at NAB in Vegas 2018.
And Vox Pro is brought to us from the folks at Broadcasters General Store. We appreciate them. It's easy to contact Broadcast General Store. Maybe work yourself out a demo or find out your pricing on Vox Pro hardware and software. Contact Broadcaster General Store on the web at bgs.cc or call them at 352-622-7700. Any of the folks at Broadcaster General Store can help you out. I've been dealing with them for years. I mean, like, back since my Sam Phillips days when I was doing engineering for Sam Phillips in Memphis, Tennessee. Call them at 352-622-7700, Broadcaster General Store. Thanks a lot, bgs.cc, for sponsoring This Week in Radio Tech. All right. Hey, guys, we've got a lot of ground to cover, so let's just kind of jump right into it. PTP clock. Now, I first became familiar with the idea of synchronizing devices around a broadcast facility with the old Genlock signals in a TV station, where in a TV station, no matter where the video is coming from, the idea is to have it arrive at the switcher at the same time. So when you switch from one TV camera to another, or to a videotape recorder, or a film chain, a camera on the film chain, that you were making that switch during the vertical interval. And so everybody had to be coordinated. And back in the older days of TV, or maybe at your high school TV station, things weren't synchronized. So whenever you switched cameras, you got that roll in the video. Well, that's what happens when things aren't synchronized. Then we came along with audio, and we had to synchronize audio devices using AES word clock. I remember that. I didn't implement any of that myself, but plenty of stations did, where they put in an AES audio system. But now we're into IP audio. And I got to hand it to my guys at the Telos Alliance for inventing Livewire, which was the first practical way to get audio over IP that was low latency and routable. Prior to that, you couldn't really do it. You'd talk in your mic and you might hear it back a little while later in your headphones, and that wasn't going to work. So low latency and routable is what Livewire brought to the table. Almost 20 years ago is when they got started working on that and figuring that they could do it. So, we had to invent, the guys at Livewire, at the Telos Alliance, had to invent a way to keep everything synchronized. And I tell you what, I'll give the 30-second or 1-minute overview on that, and then I'm going to let the inventor talk about that. We've heard it said on this show before that a man with two watches never knows what time it is. Now, if you got one watch, you may be slightly wrong, but you know what time it is. But if you got two watches, you never really know for sure. In fact, you may notice this clock right here usually runs a little fast compared to real time. And once in a while, I have to go, reset it, back it up a couple of minutes or so. And in a digital system, it's important in many cases that everybody, all the devices on the network, know what time it is. But what's the first critical thing is that every device has to know how long a second is. and I say a second, I mean, they have to know how long a millisecond is. They have to know how long an hour is. But if we take a common standard like a second, and we know how long that is, then every device on the network can agree on what they're doing in that 1 second. For example, if you have a bunch of devices that have to sample audio 48,000 times per second, all those devices need to agree on how long a second is so they can divide it up into 48,000 equal parts. If we don't do that, if everybody has a free running oscillator, if every device has a little bit different idea of exactly how long a second is, but every one of them is dividing up into 48,000 parts, well, you're going to get some device over here that is making 48,012 samples every second. And you're going to have a device over here that's listening for 47,993 samples per second. And the two aren't going to agree on that. And every once in a while, you're going to get a glitch. There's going to be an underrun or an overrun, and that's bad. We want to keep everybody into perfect agreement as to how long 1 second is. So when we divide it by 48,000 or whatever our sampling rate is, say for video, we all agree on exactly how many that is in 1 second. So that's why it's critical that everybody be synchronized. Now, I'm going to turn this over to Greg Shay. Greg, have I got that sort of right, or is there something I'm missing in that explanation?
Yes, Kirk. Everything you said is right. And actually, it's a good segue to talk about what is different with PTP, because as you mentioned, a lot of years people have been connecting synchronization cables so that different devices would be using the same sample rate. PTP goes one step further. It's not so different. Did you ever buy one of those atomic clocks that listens into WWV on the radio?
Yeah, in fact, I've got one 4 feet away from me on the outside wall of my office here.
So in principle, PTP is not so different than that. But instead of listening over the air, it's listening on the network. So the job of PTP is to give every device knowledge of what time it is. Then, if everybody has a perfect clock or very accurate clock, everybody can derive a sample rate, and if it's video, it's 2997 or 30 hertz. If it's audio, 48 kilohertz, or any other sample rate. Whatever you need, you always have this master time reference underneath, which is being communicated over the network. So that's probably the first thing, because we've all used synchronization for a long time. And as you know, you typically would have your master blackburst generator, in a facility. That's telling everybody where the video frames are and where the audio frames are. But the old way of doing it never communicated time down to the nanosecond, actually, PTP does. So it's communicating time to everybody. Everybody has an accurate clock. Everybody synthesizes the sample frequencies from that clock. Everybody matches.
Mm-hmm. Okay. There was I think one principle we should establish actually has to do a bit with a patent that has been granted to you, Greg, some years ago, and that is the idea of sending very precise time indications over a network that is jittery. So ideally you want your path where you're sending, hey, this is exactly what time it is. This is exactly what time it is. Ideally, you'd want that path to be super accurate. But we needed to come up with a way to establish that accuracy over a network that could have little bitty problems. And so kind of tell us about how that process works, because the same process applies then to PTP and other standards that do the same kind of thing.
Sure. So what you're jumping into is actually a detail of how do you make this stuff work in the real world. And as you described, the problem is the packets that go between switches and go over different lengths of network don't arrive instantaneously. So you have this delay, and then the variation in delay, you can call it jitter. Another way to think about that is if you're measuring time, if you're communicating time, then this is time noise. So it's a noisy signal. just like any other noisy signal. And in fact, when you get into the actually looking at the data, you're trying to recover an accurate measure of time from noisy samples of time. And in principle, it's no different than noise of anything else, than a noisy audio signal. And as you may know, it's very difficult to get rid of noise once it's in your signal. So what you're asking about is, this was a technique that, as you mentioned, our goal in the beginning was to do very low latency audio. Low latency audio means you don't do very much buffering. Not to have very big buffers, you have to have very accurate synchronization. Otherwise, you flow over the end of your buffers and have clicks or pops. So from the beginning, we knew we needed an accurate synchronization. And by the way, this was about 3 years before PTP came out. I always say, if PTP had been around and available, we could have used it, but we're just a little bit ahead of that curve. So the mechanism that you're talking about is a way of filtering the packets and figuring out which ones got through the network with the least amount of delay, and then which ones, were delayed. The basic principle is this. A network can never make a packet arrive early, only variable amounts of late. So once you keep track of the times that they're coming in, you can start to tell which ones are more late, which ones are less late. And so you use the ones that are less late. Finally, there was a piece of that technology. The actual patent is based around, you can also send packets at a little bit random times, because then some of them get through. You can have many streams, many periodic streams, audio streams, video streams, and if each time you send a clock packet, it's delayed because there's a collision. It's like traffic on a freeway. You have a whole line of cars, and they're always getting in your way. Then some of them are not getting through with less delay. All of them are getting delayed. But if you send them with a certain amount of randomness over time, statistically, some of them are going to get through. And then you, at the far end, pick those out and use those.
I'm curious, these packets that are sent with a bit of randomness to them, and I get that we may get a lot of maybe I would call it periodicity in the network traffic, and so we may run into some delays there in the switches. So if you send them at a little bit of random times, you can get there just before or just after the lineup at the red light, if you will. Are these slightly randomized packets timestamped with the proper timestamp for their randomization?
Yes, exactly true.
Okay.
And we just jumped into probably the most obscure and most difficult detail, but that's okay. That's what we're here for.
This is a bit like, if you're waiting at the airport for your bag to come out. At the Nashville airport, they have this bag thing where it's got a sensor, and if there is there's a loop, and then there's this entrance to it, and if your bag comes in, and if it's going to hit a bag that hadn't been picked up yet, that's passing by the ramp again, then the ejector won't eject it onto the loop. So it puts them in there at, in places where it's not going to have a crash. Same thing for, entrance ways in bigger cities on freeways, right? Where you have a red light. No, you can't enter yet. And it waits until, I've waited a random amount of time and the traffic there may be a slot to go in here. And so you go in. So I never knew that. That's fascinating, because I can see where if you have all these devices producing audio, some video, whatever, you could have, bunches of packets or a great deal of periodicity to them, and you insert something and it could have to wait a random amount of time. You might as well establish that randomness and know what it is beforehand, then let it happen randomly inside the network. Cool.
So I was going to say, since you described the scenario, one of the ways that modern networks get the important stuff through first, of course, that's the quality of service. That's the QoS. And as things are lined up to go out on a port, it allows the high priority things to go first. And typically in a network, the clock packets, the PTP traffic, is at the highest priority, even above audio and video. So that's the other thing that you do so that they're not delayed a huge amount. I mean, if you create a big file transfer, that can be, seconds of delay as you saturate the network. So you don't want your clocking and your audio and video to stop.
One concept that we should probably cover is the notion of these clock packets, and we can start with Livewire clock packets because then PTP clock packets work similarly, and that is they're distributed as multicast UDP packets. What's the benefit of multicast, and then is there any slight downside in UDP or an upside to UDP? What's the multicast thing about?
Sure. Multicast is a really convenient way for everybody to receive the same message. And of course, if you're trying to have all devices synchronized to one source, it's a natural way to spread the clock. So it's like a distribution amplifier. Everybody gets to hear those messages. Really, the only downside is that wide area networks typically don't route multicast. So when you're going between your sites, between buildings, between cities, modern fiber optic networks are starting to make that just as fast as anything you have in your facility because of the way that the wider area networks are managed. It's really a management decision. They usually don't allow multicast, or they very severely restrict it. So that's the case that you would use unicast. PTP works either way. It's typically now done multicast.
So in a multicast system, it's different than broadcast packets, because when I first started studying this PTP stuff, I thought these were broadcast packets and they just went everywhere. And thank goodness I talked to you, because you said, no, these are multicast. So they only go where they are requested to go. Like an end device says, hey, I'd like to receive those multicast packets. Is that about right?
Yes, exactly. So this is the protocol is called IGMP, Internet Group Multicast Protocol. And that's a mechanism that devices ask for, essentially, and that you ask for it by multicast IP address. And it's an IP address like anything else. It typically starts with 239 dot, so it's just an address space that they have reserved. And as a device, you send out to the network, hey, I want to hear this particular, think of it as a channel, multicast address. And then the network, meaning the switches and the routers, make sure that when those packets come along, they send you a copy.
So Livewire clock has always worked this way, multicast IGMP packets, and PTP works this way as well, right?
Yes, right.
Okay.
PTP has the option. Interestingly, today we're all working with PTP version 2. If I get my dates right, I think version 2 dated to about 2007. They are now working on PTP version 3.
Of course.
Dirty little secret of the industry. If you go look up the PTP unicast stuff, some of it wasn't perhaps fully baked or fully specified, which is fine. We've gotten by the last 10 years without it. Another point we should probably mention here is you have a choice to try to spread your clocking information, PTP, over these wide area networks, like I mentioned, between cities or between your facility. And the other choice you have is there's this very nice satellite-based way of transmitting time or synchronizing time everywhere, of course, GPS. So your other choice is you just put a GPS receiver at your facilities, and commonly available are PTP master devices that have a GPS input. So that's generally how you want to synchronize at the wide area or even globally, rather than try to deal with the additional delays of the long distance and compensate for that.
So let's before we take our next commercial break, let's talk about that for a minute. So a facility, and I'll go ahead and throw out this term here. We can better explain it as we go along. But there's this a device that a bigger facility might have called a PTP grandmaster clock. Boy, that sounds important. It sounds like the top guy in the judo class, man. So the grandmaster clock, and typically a grandmaster clock can operate by itself, or you can hook it to a GPS receiver, and therefore it will be a slave, or it'll get a time reference from GPS satellites, which are extremely accurate. And your neighbor down the street, in the next town, in the next state, or on the other side of the world gets exactly the same reference. Is that about right? Yes, you're right on the ball there. Okay. So tell us, before we go to break here, give us a minute or two on what else are we talking about when we talk about a PTP Grandmaster clock? Okay. So the PTP Grandmaster is the device that sends out all the clock packets, telling everybody else what time it is. It describes itself. So inside PTP, there's this algorithm called the best master selection algorithm. So you can have redundant clocks. You can have multiple sources of clocks. But since they describe themselves, and there's this whole scale of quality. So if you are connected to GPS, that is considered a very high quality, a very accurate source. You may have a backup clock that, I don't know, if your GPS antenna came unhooked, you don't want to be off the air. So it will fall back over to a non-GPS reference, and then you may have a, redundant of that. So there's a whole process that you can have redundancy. They stay out of each other's way. Everybody knows who they're listening to, who they're supposed to be listening to. One more thing that PTP has is if you're interested in very accurate absolute time measurement, each device can essentially ping the Grandmaster or ping an intermediary boundary clock and say, how much time did it take that packet to reach you? And then send me back that information. So you can effectively compensate even for the time of flight of the last bit of the network between you and the PTP Grandmaster. So this is the way that you home in on an absolute phase of time as well as frequency. I tell you what, after the break, I want a little bit more explanation of that. That sounds pretty cool that devices, if they need to, not every device needs to be that accurate, but if they need to, they can ask, how long did this take to get to me, so I can compensate and crank my clock forward just a bit. All right. Hey, this is This Week in Radio Tech with Kirk Harnack. Chris Tobin is along. We've been talking with Greg Shay, but also Sean Dolan is along too. And after the break, we're going to hear about this transit delay compensation thing or correction thing. And then we're going to talk with Sean and with Greg and Chris about, some of the practical implications of PTP clock. And also as it relates, since most of us are radio engineers, as it relates to maybe smaller radio station networks. When do you need PTP clock? When do you not? Just what's important there. So that's what we're going to get to in the second half of our show. This Week in Radio Tech, it's episode 432. We're brought to you in part by the folks at Calrec. Let's hear from them.
Calrec's Type R is a modular, expandable IP-based radio system featuring 3 slimline panels, a fader panel, a large soft panel, and a small soft panel easily configured to give the operator full control. Layouts are saved and recalled quickly between shows. A single 2RU core with integrated I/O gets customers up and running fast, and that single core can power up to 3 independent mixing environments with no sharing of DSP resources. Available in 4 DSP packs, and as your station grows, larger packs can be added, enabling it to grow with you. Power to the surface is supplied via standard PoE switches, keeping cabling to a minimum. Type R is fully AES67 compatible, as defined by SMPTE 2110, which means that it is also compliant with NMOS discovery and connection management specs. All these features combined make Type R the most flexible radio console you can buy. Find out more at calrec.com/TWiRT.
And welcome to Calrec, a new sponsor here at This Week in Radio Tech. Go to calrec.com/TWiRT, calrec.com/TWiRT. Studio guests are only human, and humans cough, they sniff, and they clear their throats, even on the air. You can cure this with Angry Audio's Guest Gizmo. Press the cough button, mute the mic. Every guest needs one of these. You know what else guests need? Well, they need headphones, which is why each Guest Gizmo also has a studio-quality headphone amp with individual volume control. Anything else? Well, you've seen those mic arms with built-in LED tellies. They're beautiful. But how do you light them up? Well, the Guest Gizmo does that too, illuminating the red light whenever the mic is on. And installing the Guest Gizmo in your studio furniture couldn't be easier. You need one of those, a 2 3/4 inch hole saw and a steady hand. No router required. Your studio gets a clean custom appearance and you get all the credit. Check out the Guest Gizmo and all the other cool gadgets at angryaudio.com. Angryaudio.com. They got a lot of cool stuff there, so check it out. All right, it's This Week in Radio Tech, episode 432. I'm Kirk Harnack, along with Chris Tobin and Sean Dolan and Greg Shay. Now, we got one more question for Greg, and then we're going to talk about some practical implementations of this tech. So, Greg, you mentioned this transit delay correction or compensation. So give me just a little bit more detail on how that works and what kind of gear might want it, because I understand that audio gear probably doesn't need to have that.
Yeah, so terminology. So the official name for this is called a peer delay request. So it makes sense. You're asking your peer to find out the delay. So you make a request, and then there's a peer delay response, which comes back.
Okay.
And so one in terms of who needs it, it's important to understand that PTP is it's a global standard, and it's used for more things than media. In fact, the media industry embracing it has been fairly recent with AES67 in 2013, and it was around for 10 years before that. Some of the industries which have made use of PTP is, for instance, industrial automation, where you're needing to very precisely control, let's say, multiple robot arms on an assembly line, and you need to coordinate things so they don't smack into each other. One of the other places, interestingly, is on Wall Street, where if you get your stock trades in, milliseconds or even microseconds sooner, you get the deal. And believe it or not, that is a serious user of PTP. When you need to know down to microseconds and even nanoseconds, the fundamental units inside the PTP protocol are nanoseconds. So that's 10 to the 9th. So that is a billion, 1 billionth of a second. So just for comparison, the speed of light in 1 nanosecond, light goes about 9 inches. That's about that long. So when you have a fiber optic network and you're in Wall Street and you're across the street, that's a bunch of nanoseconds. That means if somebody has a shorter cable than you, they can beat you to that punch. So they're serious about this. So, and as you know, if you're too, some of those things, if you're too soon, then you're not in. It doesn't count. So that's where, if you need absolute phase information. So in an audio sense, so let's say, I don't know, on a LAN, the typical delay of a packet across the LAN, let's just say it's 20 microseconds. That's 10 to the minus 6th. That this feature of PTP would compensate for. 20 microseconds is about 1 audio sample. The speed of sound in air is about 750 feet per second. So roughly speaking, it's about a foot per millisecond. Mm-hmm. So then 1/20th of that, actually 1/50th of 1 foot is, doing my math right, I thought it was about 1/20th of an inch. So 1 audio sample of delay is about your perfectly set up stereo speakers, your phased stereo speakers. One of them is 1/20th of an inch closer to you than the other. It's not really audible. It's not that important.
And that's about a 1 sample difference then, isn't it?
Yes.
Wow. So I never thought about it.
You got to kind of get it. Yeah, you got to kind of understand the scale of these things. Now, obviously, you don't want a big phase delay, but generally your modern networks don't give you that much delay. So it's on that basis that I've often said, you don't really need the peer delay mechanism in PTP to get perfectly good audio.
But there are applications where you would need it. But for those of us building radio stations, we probably won't encounter devices that need to have this. I guess there may be some devices where that's maybe turned on by default or turned off by default, but at least in terms of the gear that you and I are familiar with from the Telos Alliance, we don't do this because we don't need it, right?
Yeah. One of the factors is, again, it's a little bit esoteric, but if you are recovering an audio sample clock, what is important for the fidelity of your audio is that your audio sample clock is stable, that it's not wandering and hunting around. Well, it turns out that if you're using this stream of clock packets to recover your audio clock, and you're also trying to send and receive these peer delay requests and make compensation for that, think about it. You've got 3 sources now of time error or time noise to factor in. So the funny paradox is, for audio, for a stable audio clock, the peer delay mechanism can actually make things worse. So it all depends on what you're trying to shoot for.
If you could, let's cover one more tiny thing. If your PTP clock, or in the case of like a Livewire audio over IP network, if they're not referenced to an external source, I think we might call that arbitrary clock, or at least that we have arbitrary clock offered in the Telos X nodes, and for a network that doesn't connect to stuff on the outside world, if you're just talking about a local facility, you may not need to know what actual time it is, but you really, really need to know how long a second is. Is that what arbitrary clock does?
Yes. So what you're talking about is, the Telos, the Axia X node product does not have a GPS receiver, nor does it need one, nor is it often located where it would be convenient to have a GPS antenna. So if you need to, you can use it as a PTP master. And just as you said, it uses this mode called an arbitrary clock. That doesn't mean the clock's arbitrary, but it means that the reference, the 0 point, it doesn't know, the date. It doesn't know the global GPS. That's actually the atomic clock, because the GPS system is tied to this global atomic clock reference. As long as everybody on your facility, all the devices are using the same clock, this goes back to how we used to do sync. You ran the sync cable around. As long as everybody's on the same clock, you're good to go. If you want to send and receive media real-time live between your facility and somebody else, and they are referring to real-time, then that's when you need to have a common time base using the GPS clock.
Gotcha.
As your PTP master.
I think we've got a pretty good foundation here for understanding what we're talking about, and we're going to have to do another show down the road, talk more about implementation. But Sean Dolan's been standing by at the Philadelphia airport in an office there. Sean, thanks for doing so. Sean, you've got some experience with building AOIP networks with Livewire, and you're just getting introduced to PTP clocks. Talk to me about what you've heard Greg say, and mix with your own experience, and tell us what you can about synchronization, Livewire, and PTP clocks, and what your thoughts are right now.
Yeah, it's so funny to hear Greg talk about PTP clock and talk about clocking in general, and to think that it actually works so well in the field. That's the incredible part, that it's so consistent and so well implemented that it can work in facilities everywhere. The way I end up describing it to most people is that, like clocking, to dumb it down from everything that we've talked about here. Our clocking is like getting the gears of 2 pieces of machinery to line up. If your clock packets aren't making it through on the network, those gears are going to be different sizes, and of course you're going to not have them mesh together as they should. So that's the part that is difficult to sometimes get certain people in a facility to understand. But once they get that, they understand the importance of classes of service, setting up their switches properly to allow for PTP or Livewire clock to actually pass through properly.
So one thing I'm wondering about is sometimes we connect different in the radio biz. We connect different facilities together, and I'm going to go back to Greg on this because Greg. Typically, when radio facilities get connected together, for a couple of decades, we used ISDN, and ISDN did have a clock reference at the phone company, if I'm not mistaken about that.
Yes.
But nowadays we're using IP codecs between places, and I don't know that I've got a Zip 1 over here behind me. Some people may have a Zip 1 or a Barracks box or something from Calrec, and they use this to send audio to and from a remote side, a ball game, or maybe a voiceover studio, a remote voice talent, or another radio station. And I'm guessing that these two codecs really don't have a means to be locked with each other. How do they avoid, or even do they avoid, having underruns or overruns?
Sure. So, yes, you're putting your finger on, you make good observations. And yes, in the ISDN world, you had this guy in the middle, the phone company, that was the clock master, and they took care of that. And that is the way that ISDN, the classic Black Zephyr, and actually the Zephyr Extreme as well, they used that clock from the ISDN to slave everything to. So that's how that worked. You were right with the Zephyr IP was the first time now that was not present. So the trick the trick that the IP codec did before PTP was around is you're essentially implementing a time-based correction at the receiving end. So what you did was you manipulated the audio, and now what's happening there is two things. There's a very subtle FM modulation as you're very subtly speeding up or slowing down the audio sample rate in order to manage that, so you would not get audio crashes. And if you remember the early days of webcasting, prototype of before like what we're doing here, you would listen, and if you were to listen to an audio program long enough, it would stop and rebuffer and then start to play again. That's before they figured out this mechanism. The downside of the time-based correction or the sample rate conversion algorithms is that takes a buffer and some more time, and that's one of the things that adds into the latency of a codec doing that. And as you know, IP codecs, and the data compression codec added more latency, typically tens or 100 milliseconds. Nothing like the sub-millisecond or 1 or 2 millisecond latencies that we're talking about for these live streams.
Hey, I want to ask Chris Tobin. Chris, you and I have been sitting here learning from these two guys, and I know on a previous episode you talked about the One World Trade Center having an array of GPS receivers on the roof, that you had been part of a project to put these things in, and the data from these GPS receivers is available to tenants, technical tenants in the building that need such signaling. What can you tell us about that system and how people are using it, how broadcasters are using that?
It's very straightforward. It's not as crazy as you might think. It's a standard GPS distribution. The 4 different or 5 different receivers, actually antennas, are designed for diversity, just like any facility. I mean, there are many broadcasters here in town that have more than one antenna on the rooftop, and they also make sure they have different paths back from the rooftop down to their broadcast operations center. So at One World Trade, it's basically a distribution panel. You take the GPS pulse. We have various forms of how you can grab it and sync it over fiber or copper if you choose, and then from there you just use it as a clock, as timing reference. There's no one particular way it's used. It's pretty much standard stuff. The nice thing is it's one facility. It's maintained and operates one setup. So you don't have, like a porcupine effect of 2 dozen antennas on the rooftop or in a window trying to provide timing for somebody. Then all of a sudden it goes out because, the window shade came down. Trust me, I worked for a place where we had that happen at one of our locations. So the broadcast folks, One World Trade decided, let's have one master system, make sure it's redundant in many ways, and everybody can rely on it, and that's what they do. And that's, to Greg's point of timing and what you need at the end, how to use it, where to use it, what it's used for is important to understand that. And I think we take a lot of things for granted. If you're familiar with, say, the new tech product, TriCaster, and the NDI protocol that's available, there's a lot of things in that helps you to time devices and move things around and connect. But they're limited by certain things, which is the hardware that you're working with. But again, it's still timing. We just take it for granted. We don't even think about it. You have multiple IP cameras coming into a box that's switching, and nobody even bats an eyelash as to how it's happening and making sure it's in proper time. But I was mentioning earlier that I was talking to somebody recently about PTP, and boy, wouldn't it be nice to know that you could be in locations around the globe and be distributing and moving traffic back and forth, whether it's audio and video, and knowing that the time is the same wherever it's going. Where in the past, as Greg pointed out too, if you had a sync cable running around your plant, okay, everybody in the plant is synced, but then all of a sudden you have something coming in from the outside, maybe via satellite, maybe via a DS3, and all of a sudden your video is like something's not right. PTP timing allows you to do a lot of things that in the past we either couldn't do because it was just hard to do. It just was impossible. Now it's a question of, okay, what can we do with it? How do we make it better?
Chris, I know you're in a variety of facilities. Are you seeing PTP Grandmaster clocks installed in places yet?
I'm starting to see PTP popping up. I mean, a couple of years back, AVB was what I was met some folks with, which was I guess it's a version of PTP. I gotta be careful because I know it's changed names and the standards and stuff. But that was the first iteration of let's make timing perfect. And I remember working with a couple of folks and talking to people at 2 sports networks that were looking at product. And at one of the NAB shows, I was walking with one of the engineering supervisors, and he's like, "Well, I'd love to buy that switch, but it doesn't support AVB, so we can't use it on a new digital plant. Gotta go." And I'm like, "What the devil is going on?" And that's when I started talking to Everts and a few other folks, and like, oh, here's what's coming down the pike. And it was interesting, their deployment, how they wanted to use it, what they were doing with the 1000 by 24 video switch, and the timing that was required for switching between sources and destinations. I'm like, AVB, PTP, all this stuff's coming down, Aspen and all the other stuff that's happening. So it's pretty wild what's going on, what we can do. Just imagination is the key.
I'm going to circle back around to Greg in a minute, but I want to ask Sean. Sean, you're mostly in radio facilities, but are you seeing any of this PTP stuff yourself yet?
Oh yeah, absolutely. I definitely see it being used. Like we mentioned, the X-Node has can be used for PTP clock, although undisciplined.
Yeah.
But I have seen people use actual grandmasters that are referenced to GPS. Even for smaller systems, they sometimes prefer to do that, just in case they want to expand or perhaps do something across different lands in the future. So, absolutely, I definitely do see it.
Well, I know we're going to see a lot more of this in broadcast facilities, especially, and who knows exactly where the topology and the business model is going to go, but I got a feeling that we're going to see more broadcast facilities within the same company, linked to each other and linked to each other in such a way that they want low latency, they want swift interaction between sites that are remote, and they're going to want to do this over what's becoming more commonplace, just really good, fast, reliable fiber internet or private WAN connections, and those are going to have to be synced with each other so they can get all that performance. Greg, Chris brought up this question because I remember AVB, and I haven't heard much about it lately, but I remember AVB talking about IEEE 1588, which is the PTP clock. What can you remind us about that relationship?
Yes, it actually is the same. AVB used PTP version 1. In principle, that works the same way. If you go and look up the specifications, AVB, I believe it was 802.1, and the 802.1 AS stood for their synchronization, and that basically said, okay, we're going to use PTP. So the other thing that people may be familiar with is network time protocol. That's been around a long time. Many computers have a setting. I know, I think Windows does.
Sure.
Where you can just say, synchronize my computer clock using network time protocol. So it's helpful to describe why we were not able to use NTP. NTP goes all the way back to, with the internet. I know of it from the 1980s, mid 1980s. So it typically is reaching maybe 10 milliseconds of accuracy. And they thought that was doing great. If they got into single milliseconds, that was fantastic. So PTP came along and said, okay, our finest accuracy is in the nanoseconds. It's just organized in a way to allow you to get the higher accuracies if you need. Whereas NTP, we actually tried this here at Axia in the beginning. We tried using NTP for Livewire sync, and we just found that 10 milliseconds of accuracy was not enough.
I just happened to look at. We'll put a link to this in the show notes, but I just happened to look and see that NTP was designed by an engineer named David Mills.
All right,
David Mills, and does NTP time and PTP time, did they both start at the same time back in like 1970? I thought both these were counting seconds. Okay. Yeah, so counting seconds since 1970.
Yes. And there's a quirk. The quirk is your common ordinary time. What time is it? Look at an atomic clock, and that has a time. That is called universal coordinated time. PTP does not use that time. It uses what's called TAI time, which is the International Atomic Time. And the difference is our everyday universal coordinated time has the leap seconds in it. So since 1970, it turns out there's been 37 leap seconds. So leap seconds means the Earth is slowing down the rotation. So they want to keep that time at midnight so the stars are lined up and so on and so forth. Trying to do math calculations with a time reference, including these sort of weird arbitrary leap seconds, and they're going to add more. That's tricky. That's bad. That's worse than color frame burst clock. The way that NTSC. 2997, not exactly 30 frames per second.
Yes,
that's complex enough. So the PTP time reference uses this number of seconds since January 1st, 1970 without the leap seconds. And currently it's 37 seconds ahead. Just a little bit of bizarre trivia.
That's quite a phase difference there.
I know. No. So here's a true story, if it's interesting. The very first time that we tried to connect a piece of Axia equipment to a piece of Ravenna equipment, and we were both using PTP, one of us was off by 37 seconds.
Oh, my goodness.
You can guess the mistake that somebody made, and I won't fess up to say who made that mistake.
Wow. Well,
but we fixed it.
Yeah.
We fixed it quickly, but it was like, what the hell is going on? 37 seconds.
It's almost like different space agencies using imperial units or metric units, So
yes, and you tend to crash Mars landers that way, right?
Exactly. Hey, I want to tell you what, we're going to take a break in just a couple of minutes, our last break. After the break, I'm going to ask each of you for a tip of the week. If you've got a resource, a web page, a book, something that our listeners and viewers can go to get more information about this, I would appreciate that. So in this time, why don't you be thinking of that? Sean and Greg, I'm going to ask each of you, and Chris, I'll ask you too, for some kind of resource or an anecdote or something that people can take away from this podcast about PTP clock and what they'll need to know. Our show, This Week in Radio Tech, episode 432, is brought to you in part by our friends at Lavo. Let's hear from them. Be right back.
There has probably never been a better time in history to buy a new radio mixing console. Today's consoles are more sophisticated than ever, with more features and functions than you can shake a stick at. But have you noticed how complicated they are? There's a sea of knobs and switches and displays and buttons. Some of them look like you might need a pilot's license to do your show. Well, a board doesn't have to be complicated to be powerful. Just look at the new Ruby mixing surface from Lavo. The first thing you notice is how smooth and streamlined it is. Ruby has lots of cool tech, but what it doesn't have is that confusing ocean of buttons that clutter things up. Now, we all know that there are some console features the jock only uses once in a while. So why dedicate controls to them? Ruby fixes this problem by moving those once-in-a-blue-moon controls to a touch-sensitive, customizable GUI that happily shares screen space with your other studio software, helping you fight control room clutter. Thanks to this design innovation, talent that use Ruby produce smoother shows with less errors. Controls that are used the most fall naturally to hand, while functions that rarely need adjustment are easily controlled with just a couple of clicks in the context-sensitive GUI. And Ruby has cool features you won't find on other boards, like Auto Mix, an intelligent gain writing function that guarantees the perfect mix for multi-mic morning shows and call-in segments. Dual mode snapshots that instantly switch the motorized faders between on-air and production modes, and enough DSP and I/O options to make even your pro sound pals green with envy. And because quality is as important to Lavo as it is to you, every console is proudly built to fanatically precise standards at Lavo's own factory in Germany. If you're ready to declutter your control room, do yourself a favor. Check out the new Ruby and the other cool Lavo radio tech at www.lawo.com/TWiRT.
And thanks a lot to Lavo for sponsoring our show. Be sure you check out their gear. And when you do, go to lavo.com/TWiRT. It'll take you right to the radio gear and let them know that we sent you there. So thanks a lot to Lavo. Hey, it's our final few minutes of This Week in Radio Tech, and we've got a few tips. I'm really excited about these because I've got a heads up on one of them. Greg Shay, you've found this amazing free utility that tells about PTP. What is it?
Yes. So I can't take credit for finding it as much as being part of the AES67 plug fests, which ever since the standard was published, we've gotten together. And this company, excellent company, MEINBERG, spelled MEINBERG, they make, they're one of the vendors of PTP grandmasters, and they make this fantastic tool called the PTP Track Hound. And Kirk, I put into the chat window the link to it. And what this does is you just run this on a computer, and basically, because PTP is multicast, this tool monitors who's around, who's listening to who, how many grandmasters, what time do they say it is, what's going on. It helps you debug and diagnose PTP problems. For instance, if you have conflicting masters due to misconfiguration or whatever, your device is trying to synchronize, get lost who's supposed to be the master. At a glance, lots and lots of really useful stuff, as well as, you're learning about how PTP works. So just for that reason alone, it's a great tool, free. What more can you say?
We will put the link to this in the show notes. So go to, by the way, all of our show notes, the best way to find those is to go to our website or to the GFQ's website. Go to thisweekinradiotech.com or gfqnetwork.com and look for our show. Of course, my website, that's the only show we have. If you want to find out about more cool shows, you can check out the GFQ Network's website. But we'll put this link in the show notes. But if you Google MEINBERG, MEINBERG, PTP Track Hound, that's the name of this free software. All right, cool. Greg, thanks for that tip. Sean, you are new to the Telos Alliance, but you're not new to broadcasting and broadcast engineering. Maybe you can pass along a tip for our listeners to give them something to think about.
Sure. Well, it's funny that Greg even mentions MEINBERG, because my suggestion was that MEINBERG has a really great informational series on what PTP is. Explains all sorts of things, from what an ordinary clock is to what a grandmaster is, to how a switch can act as a boundary clock, and things like that. It's really interesting. So when I first started hearing about PTP, I believe that was a series that I found to be really informative, that I have passed on to other people as well who have asked, especially when getting into some of the Telos Alliance products that use AES67 and can use PTP. When they ask, what is PTP? MEINBERG has this great series that I'll send to you shortly that is gets a great introduction to PTP.
That would be awesome. Yes, indeed. If you just Google MEINBERG and PTB or IEEE 1588, then you'll see a lot of results there. But yeah, I'd like to see exactly the series that you're talking about. So we'll put that into the show notes. Chris Tobin, you got a tip for us this week?
Well, real quick tip. It's easy. It's the reasons we have sponsors is not only to help pay for what we do, but also to educate and inform people. So Calrec has a document. It's called, let me see if I got this right, Beginner's Guide to IP. I've been reading through it last couple of days. It's pretty cool. It gives a lot of basic information and sort of makes you think about what you're doing and how you're building out your networks and what to expect. And they mentioned in their video as well, and they talk about SDI, Serial Data Interface. Many of you have used it or maybe not, or maybe you're just starting to do multimedia at your radio station, have these cameras that have a BNC connector on them. Go, oh boy, SDI, I got to convert it to HDMI, plug it into my computer. Well, there's a lot of products now that are doing IP video, and you have timing issues and concerns because you're doing multiple cameras, multiple things. So this document talks about that and how everything in their product line talks to and understands timing. So I'm just suggesting that you should take a look at that along with the other two suggestions from Sean and Greg and say, hey, okay, this is what it's all about. And it's just like back in the day, if you were doing television, it was GenLog. If you're doing radio, it was AES word clock. And now it's radio and TV in the same place. We're all doing the same thing. Time to learn all sides of the fence. And I'm telling you, it's pretty cool because once you start realizing what you can accomplish, man, it's just fun. It's just having a great time.
I found the document. We'll put a link to it in the show notes, and it does look pretty good. Beginner's Guide to IP from Calrec. And I'll go ahead and add one. For quite a few years now, we've had at the Telos Alliance a pamphlet, a book. That's called Introduction to Livewire, and it's version 2. something right now. So I will put a link to Introduction to Livewire, and the principles, even though it talks about Livewire, the principles there are either the same or extraordinarily similar to the principles that you need to understand for AES67 and SMPTE 2110-30 and PTP clock. So if you learn about that, you'll pretty well know about the others too, or you can apply those same principles. We got to go. And first of all, Greg Shay, thanks on short notice for saying yes and joining us. I really appreciate your expertise.
Thank you for having me, Kirk. It was always fun to chat with you.
Great. And the great thing is, Greg, this information, I know that you study this, you learn all about it. You can pull facts and figures out of your heads and tell us about concepts. But it's great when that information can leave your office and hit thousands of people who need to know it. So it's a great service. So thanks for sharing your knowledge with us.
Sure.
Also, Sean Dolan. Sean, I'm sorry we didn't get to talk to you very much, but I look forward to chatting with you again. You and I are going to finally get to, well, I guess shake hands at the NAB. I guess you'll be there, will you?
Right. I will be.
Okay, good. And then we'll have you back on the show. We're going to talk about, well, whatever's hot in your mind for broadcast engineering. I know I've seen some of your work, and especially you're hired on to be at least part of your time as an expert in IP telephony, and that is an area that's still a little mysterious to some people, especially the SIP technology. How do I, what talks to what, and how do I get that to happen? And even for me, I kind of stumble my way through it, and luckily it's not too complicated, but you just got to learn about how it functions.
Yeah, that's right. It's definitely a huge area to explore. And thank you for having me on the show. It's been a pleasure. And it's also been a pleasure learning from Greg, as always.
And it's great to spend time with both of you. And Chris Tobin, man, I know just before the show you were off in some secret location that you really couldn't tell me much about. But I'm glad you made it to a safe place from which to join us.
Yeah, I'm actually working on 3 different projects, and 2 of the 3 were in that one building location we spoke at earlier. And I got back to a place I could sit down and relax, have a cup of coffee, and not the noise of blower motors from transmitters and all kinds of things going on. But thanks a lot for Greg and Sean for coming on and helping everyone understand. And I always love the way Greg talks about the technology and says, well, if you think of it like this and look at it like that, but go back to that time when these things didn't really exist this way. And now all of a sudden, here we are. It draws you in. I love it because when we've been on a couple of panels together, and when he talks about something, it's like, this is what's important for people to understand. You got to look at it from not just the numbers or the digits. It's like there's more to it. And then Greg's about doing that. It's great stuff.
Greg explains things well. You know, if I'm ever on trial, and Greg can be an expert witness that supports my innocence, I want Greg as the expert witness, right?
If you go on trial, we're all gone. You will find us.
All right. Hey, I want to say a big thanks to Suncast. Man, this guy, Absolutely. What a producer he is. He deals with stuff on the fly, last minute changes. Suncast, thank you so much for producing our show this week in Radio Tech. From the bottom of my heart, I can't tell you how much I appreciate the work that you do. Also, thanks to Andrew Zarian, the founder of the GFQ network. Without him, well, we'd be somewhere else. And it's a lot of fun being here. See, it's so much fun. I even have the t-shirt, Subway, Guys from Queens, GFQ. Thanks to our sponsors, too. Be sure you go visit them. It really does help us, and you might help yourself, too. All the sponsors on today's show, 5 of them now, if you include the TELUS Alliance. So speaking of TELUS Alliance, live from their studio, my studio, their studio in Nashville, Tennessee, I'm Kirk Harnack. We're going to be back next week, and our guest, Peter Fimal, will be back here next week. He got pulled away this week, and that's why he's going to be on next week. So Peter's with Public Radio Engineering in Chicago, and he's going to be talking to us about radio engineering, especially out in the field where he is today. We'll see you next week on This Week in Radio Tech. Bye-bye.